Hello there, weary researchers of the cosmos, and welcome to another gentle journey through the deepest mysteries of our universe. I'm so glad you found your way here tonight. Whether you're settling in after a long day, curled up somewhere cozy, or simply letting your mind wander as the world grows quiet around you. Before we embark on what might be the most mind-bending exploration we've ever undertaken together, I'd love to know where in the world you're listening from and what time it is for you right now. There's something beautifully fitting about discussing the nature of time itself while we're all scattered across different moments around our spinning planet, each of you experiencing this very instant from your own unique slice of space-time. If you enjoy these thoughtful journeys into the wonders of physics and the profound questions that keep scientists awake at night, I'd be ever so grateful if you gave this video a gentle like and perhaps tapped that subscribe button. It helps more curious souls like yours find their way to this peaceful corner of the internet where we can marvel together at the extraordinary puzzles that define our reality. Now, I should warn you that tonight's topic might be just fascinating enough to keep you thinking long after you intended to drift off to sleep. But if you do find yourself lying awake at 3 a.m, contemplating the strange relationship between velocity and causality, well, at least you'll have learned something profound about why the universe seems to have such strict rules about how fast we're allowed to travel. So take a deep breath, let your shoulders drop, and prepare to explore one of the most elegant yet unsettling connections in all of physics. Tonight, we're going to discover why travelling faster than light doesn't just break the speed limit of the universe, it breaks something far more fundamental. It breaks time itself. Picture this scenario, if you will. You're standing at the edge of a vast cosmic highway, watching spacecraft zoom past at incredible velocities. Most of them are travelling at impressive fractions of the speed of light. Their forms distorted by relativistic effects, time running slower for their passengers than it does for you. But then you see something extraordinary. A ship that seems to shimmer and blur as it approaches, moving so fast that it overtakes the very light waves racing toward your eyes. This hypothetical vessel has achieved what countless science fiction stories have dreamed of: faster than light travel. It disappears into the distance in an instant that seems to defy comprehension. But here's where our cosmic fairy tale takes a dark turn. According to the fundamental laws of physics as we understand them, that ship hasn't just broken a speed limit, it has torn a hole in the fabric of causality itself, creating the possibility for effects to precede their causes, for messages to arrive before they're sent, for the future to reach backward and strangle its own past. This isn't science fiction speculation. This is the inevitable mathematical consequence of Einstein's theory of special relativity, one of the most thoroughly tested and validated theories in all of science. The speed of light, roughly 186,000 miles per second, doesn't just represent how fast photons can zip through empty space. It represents something far more profound, a cosmic speed limit that preserves the logical structure of cause and effect throughout the universe. When we talk about faster than light travel, we're not just discussing exotic propulsion systems or advanced engineering challenges. We're confronting a fundamental aspect of reality itself, the delicate relationship between space and time that Einstein revealed over a century ago. His insights showed us that space and time are not separate, independent entities as Newton had imagined, but rather two aspects of a unified four-dimensional fabric called spacetime. In this spacetime continuum, the speed of light serves as more than just a velocity limit for matter and energy. It acts as the universal speed at which cause and effect relationships can propagate through reality. Every event that occurs, from the collision of subatomic particles to the explosion of distant supernovas, sends ripples through spacetime at exactly the speed of light. These ripples define what physicists call light cones, geometric structures that determine which events can influence which other events. Imagine every moment in your life surrounded by an invisible cone extending into the future, and another extending into the past. The future cone contains all the events that could potentially be affected by what you do right now, while the past cone contains all the events that could have influenced your current moment. The boundaries of these cones are defined by light rays, travelling at the cosmic speed limit, marking the absolute frontier between what can affect what. This light cone structure creates what we might think of as the causal architecture of the universe. It ensures that causes always precede their effects, that information flows in a consistent direction through time, that the logical sequence of events remains intact across all possible observers. It's a beautiful, elegant system that maintains the coherence of reality itself. But faster than light travel threatens to demolish this entire structure. When objects or information move faster than light, they escape the confines of normal light cones. They can reach events that should be causally disconnected, creating connections between moments that should never be able to influence each other. In doing so, they open the door to paradoxes that challenge our most basic understanding of how reality operates. The mathematics of special relativity make this connection between faster than light travel and temporal paradoxes not just possible, but inevitable. The theory shows us that different observers moving at different velocities will disagree about the timing of events, particularly events separated by large distances. This disagreement, known as the relativity of simultaneity, is usually harmless when dealing with slower than light phenomena. But when faster than light signals enter the picture, this innocent disagreement about timing becomes a catastrophic breakdown of causality itself. Consider two observers, Alice and Bob, moving at high speed relative to each other. If Alice sends a faster than light message to a distant location, Bob might observe that message arriving before it was sent. From Bob's perspective, the message has travelled backward in time. If the recipient of that message then sends a faster than light reply, that reply could reach Alice before she sent her original message, creating a closed loop in time where effects precede their causes. This isn't just a theoretical curiosity, it's a fundamental prediction of relativity theory, one that emerges inevitably from the mathematical structure of spacetime itself. The faster than light signal doesn't just violate a speed limit, it violates the causal ordering of events, creating the possibility for what physicists call closed time-like curves, pathways through spacetime that loop back on themselves. The implications are staggering. In a universe where faster than light travel is possible, you could theoretically send a message to your own past, warning yourself about events that haven't happened yet. You could create information loops where knowledge appears to come from nowhere, with no ultimate origin. You could interfere with the very events that led to your decision to send the message in the first place, creating logical contradictions that seem to tear holes in the fabric of reality itself. These aren't just philosophical puzzles for physicists to debate in academic journals. They represent fundamental challenges to our understanding of how the universe maintains its logical consistency. If faster than light travel were possible, the universe would need some mechanism to prevent these paradoxes from occurring, some cosmic protection system that preserves causality even when the normal rules break down. Some theoretical physicists have proposed such protection mechanisms. The chronology protection conjecture, suggested by Stephen Hawking, holds that the laws of physics will always conspire to prevent the formation of closed time-like curves. Quantum effects, it's argued, would intervene to destroy any configuration of matter and energy that might enable backward time travel, preserving the logical structure of spacetime. But these proposed solutions remain highly speculative. We don't yet understand the fundamental physics that would enforce such protection, and many of the suggested mechanisms require exotic forms of matter or energy that may not exist in our universe. The connection between faster than light travel and temporal paradoxes seems to be built into the very geometry of spacetime itself, suggesting that it may be an unavoidable consequence rather than a problem to be solved. This realization has profound implications for our dreams of interstellar travel and cosmic exploration. The vast distances between stars, measured in light years rather than miles, seem to demand some form of faster than light propulsion if we're ever to explore the galaxy within human lifetimes. But the universe appears to have erected a fundamental barrier against such travel, not through arbitrary physical limitations, but through the preservation of causality itself. The speed of light emerges not just as a speed limit for matter and energy, but as a cosmic safeguard that protects the logical consistency of reality. It ensures that the future cannot reach back to alter its own past, that information flows in a consistent direction through time, that the sequence of cause and effect remains intact throughout the cosmos. Yet even as we confront these seemingly insurmountable barriers, the human imagination continues to search for loopholes, for clever ways around the fundamental restrictions that physics seems to impose. Theoretical physicists have proposed exotic solutions like Alcubierre warp drives that manipulate spacetime itself rather than accelerating through it, or traversable wormholes that create shortcuts through higher dimensional space. These speculative technologies attempt to achieve faster than light travel while avoiding some of the associated paradoxes, but they come with their own challenges and potential contradictions. The Alcubierre drive, for instance, would require exotic matter with negative energy density, something that has never been observed and may violate fundamental principles of physics. Moreover, calculations suggest that even these carefully constructed solutions could be used to create closed time-like curves under certain conditions. The search for faster-than-light travel has also led physicists to explore the quantum realm, where the normal rules of space and time seem to break down in fascinating ways. Quantum entanglement creates instantaneous correlations between particles regardless of the distance separating them, suggesting that information can somehow transcend the light speed barrier. But deeper investigation reveals that these quantum effects cannot be used to transmit usable information faster than light, preserving the causal structure of spacetime even at the most fundamental level. As we drift deeper into this exploration of cosmic speed limits and temporal paradoxes, we begin to see that the relationship between faster than light travel and time travel is not just a curious side effect of relativistic physics. It represents something far more profound about the structure of reality itself. The universe seems to be constructed in such a way that causality is preserved, that the logical sequence of events remains intact, that the past cannot be altered by future interventions. This cosmic protection of causality suggests that there may be fundamental principles governing the universe that we're only beginning to understand. The prohibition against faster-than-light travel may not be an arbitrary speed limit imposed by the laws of physics, but rather an inevitable consequence of the requirement that reality remain logically consistent. The ancient philosophers spoke of fate and destiny, of immutable laws that govern the unfolding of events through time. Modern physics has revealed that these intuitions may have been more profound than anyone realized. The universe does indeed seem to have built-in protections against paradox, mechanisms that preserve the integrity of the causal sequence that links past, present, and future into a coherent whole. But our journey into these cosmic mysteries has only just begun. The relationship between faster-than-light travel and temporal paradoxes opens up vast territories of speculation and investigation, from the nature of time itself to the possibility of parallel universes where different versions of causality might operate. We'll explore how quantum mechanics might resolve some of these paradoxes while creating others, how the geometry of spacetime constrains the possible, and how consciousness itself might play a role in maintaining the consistency of reality. As you rest there in the gentle darkness, your mind wandering among these profound questions, remember that you're contemplating some of the deepest mysteries that science has ever encountered. The prohibition against faster-than-light travel isn't just a technical limitation, it's a window into the fundamental structure of existence itself, revealing how the universe maintains its logical integrity across all scales of space and time. The deeper we venture into this cosmic puzzle, the more we discover that the universe has woven its prohibitions against faster-than-light travel into the very mathematics of existence. These aren't arbitrary rules imposed by some cosmic authority, but inevitable consequences that emerge from the fundamental geometry of spacetime itself. To truly understand why faster-than-light travel creates temporal paradoxes, we need to explore what physicists call the relativity of simultaneity. This elegant yet mind-bending concept reveals that there is no universal now that extends across the cosmos. Events that appear simultaneous to one observer may occur at different times for another observer, moving at high speed relative to the first. Picture yourself sitting peacefully in a train station, watching two lightning bolts strike at the exact same moment, one at each end of the platform. From your perspective, these events are perfectly simultaneous. But now, imagine your friend Alice speeding past on a high-velocity train. Due to the finite speed of light and her motion through space, Alice will observe these same lightning strikes occurring at different times. The strike toward which she's moving will appear to happen first, while the strike behind her will seem delayed. This isn't just a curious optical illusion. It represents a fundamental feature of spacetime itself. There is no absolute simultaneity, no cosmic clock that ticks the same for all observers. Instead, simultaneity is relative, dependent on the motion and perspective of whoever is doing the observing. Under normal circumstances, this relativity of simultaneity creates no serious problems. The disagreements about timing are typically tiny, measured in fractions of seconds, even for observers moving at significant fractions of light speed. The causal ordering of events remains intact because information and influences still propagate at or below the speed of light, ensuring that causes precede effects for all observers. But introduce faster-than-light travel into this delicate framework, and everything changes. Suddenly, the innocent disagreements about simultaneity become catastrophic breakdowns of causality itself. A faster-than-light signal that travels forward in time according to one observer can appear to travel backward in time according to another observer in relative motion. Consider this scenario carefully. You're standing on Earth and you decide to send a faster-than-light message to your friend on Proxima Centauri 4 light-years away. From your perspective, the message travels through space and arrives at its destination in, say, 2 years instead of the 4 years it would take light to make the journey. A remarkable achievement in faster-than-light communication. But now, consider the perspective of an observer travelling at high speed relative to Earth and Proxima Centauri. Due to the relativity of simultaneity, this observer might see your message arriving at Proxima Centauri before you sent it from Earth. From their reference frame, the message has travelled backward in time. This temporal reversal isn't just a quirky side effect, it opens the door to genuine causality violations. If your friend on Proxima Centauri receives your message before you sent it, and then immediately sends a faster-than-light reply, that reply could reach Earth before your original message was transmitted. You could receive an answer to a question you haven't asked yet, a response to a message you haven't sent. The mathematics of special relativity make this scenario not just possible, but inevitable whenever faster-than-light signals are exchanged between observers in relative motion. The Lorentz transformations that govern how space and time coordinates change between different reference frames can produce negative time intervals for faster-than-light signals, indicating that these signals arrive before they were sent. This creates what physicists call the tachyonic anti-telephone, a communication system that allows messages to be sent into the past. The name comes from tachyons, hypothetical particles that would always travel faster than light. If such particles existed, They could be used to create closed causal loops where effects precede their causes. Imagine the paradoxes such a system could generate. You could send a message to your past self warning about a disaster that's about to occur. But if your past self takes action to prevent the disaster, then the disaster never happens, which means there's no reason to send the warning message in the first place. The message prevents its own transmission, creating a logical contradiction that seems to tear a hole in the fabric of causality. These aren't just thought experiments dreamed up to puzzle philosophers. They represent genuine mathematical predictions of relativity theory, consequences that follow inevitably from the geometry of spacetime when faster-than-light travel is introduced. The universe seems to be constructed in such a way that preserving causality requires prohibiting faster-than-light travel. But the relationship between velocity and temporal paradoxes becomes even more intricate when we consider the full implications of Einstein's theories. Special relativity deals with observers moving at constant velocities, but general relativity extends these insights to include gravity and acceleration, revealing even deeper connections between motion, time, and causality. In general relativity, massive objects curve the fabric of spacetime, creating what we experience as gravitational fields. This curvature affects the flow of time itself, causing clocks to run slower in stronger gravitational fields. This gravitational time dilation has been measured countless times, from experiments with atomic clocks at different altitudes to observations of light from distant stars. The curvature of spacetime also affects the paths that light rays follow, bending them around massive objects and creating the possibility for more exotic geometries. Under extreme conditions, it might be possible for spacetime to curve back on itself, creating closed time-like curves that allow objects to travel into their own past without ever exceeding the local speed of light. These closed time-like curves represent another pathway to temporal paradoxes, one that doesn't require faster-than-light travel in the conventional sense. Instead, they arise from the geometric properties of severely curved spacetime, showing that the connection between motion and temporal causality extends far beyond simple velocity limits. Some of the most intriguing proposals for achieving faster-than-light travel attempt to exploit these geometric properties of spacetime. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, would work by contracting space in front of a spacecraft while expanding space behind it. The ship itself would never exceed the speed of light locally, but it would be carried along by a wave in spacetime that could move faster than light. This elegant solution appears to sidestep some of the causality problems associated with conventional faster-than-light travel. Since the spacecraft never actually moves faster than light through its local spacetime, it might avoid creating the temporal reversals that lead to paradoxes. The ship would ride inside a bubble of normal spacetime, carried along by the expansion and contraction of space itself. But even this carefully constructed solution cannot entirely escape the temporal paradox problem. Detailed calculations by physicists have shown that Alcubierre warp bubbles could still be used to create closed time-like curves under certain conditions. The ability to manipulate spacetime geometry on such a scale would provide the tools necessary to engineer paradoxical situations where effects precede their causes. Moreover, the Alcubierre drive faces enormous practical challenges. It would require exotic matter with negative energy density, something that has never been observed and may violate fundamental energy conditions. The energy requirements would be staggering, possibly equivalent to the mass energy of an entire star. And the creation of such a drive might itself generate the closed time-like curves that lead to temporal paradoxes. These challenges highlight a deeper principle that seems to govern the universe. Every proposed method for achieving faster-than-light travel, no matter how cleverly constructed, seems to run into either impossible energy requirements, the need for exotic matter that may not exist, or the inevitable creation of temporal paradoxes that threaten causality. The universe appears to have multiple layers of protection against faster-than-light travel, as if reality itself is structured to preserve the logical consistency of cause and effect. This protection isn't just a single prohibition, but a web of interconnected constraints that reinforce each other at every level of physics. At the quantum level, the uncertainty principle places fundamental limits on how precisely we can know both the position and momentum of particles. This quantum fuzziness might prevent the precise control over matter and energy that would be required to construct faster-than-light devices. Even if we could theoretically design such devices, quantum mechanics might make them impossible to build or operate. At the thermodynamic level, the laws governing heat and entropy might prohibit the creation of the exotic energy distributions required for faster-than-light travel. Negative energy densities, if they exist at all, might be fundamentally unstable or limited in quantity. The second law of thermodynamics, which governs the increase of entropy over time, might prevent the formation of the organized energy patterns needed for warp drives or other exotic propulsion systems. At the cosmological level, the expansion of the universe itself might limit our ability to exploit any loopholes in the faster-than-light prohibition. The dark energy that drives cosmic acceleration creates a kind of cosmic horizon beyond which even light cannot reach us. This horizon might represent a fundamental barrier to faster-than-light communication with distant regions of the universe. These multiple layers of protection suggest that the prohibition against faster-than-light travel isn't just a technical challenge to be overcome with better engineering or more exotic physics. It appears to be woven into the fundamental structure of reality itself, emerging from the deepest principles that govern the behavior of matter, energy, space, and time. But why should the universe be constructed this way? Why should reality have such built-in protections against temporal paradoxes? The answer may lie in the requirement that the universe remain logically consistent, that the sequence of cause and effect provide a stable foundation for the existence of complex structures, including life and consciousness. In a universe where temporal paradoxes were common, where effects could routinely precede their causes, it might be impossible for stable patterns to emerge and persist. The delicate chains of causation that allow stars to form, planets to evolve, and life to develop might be constantly disrupted by temporal interference from the future. Consciousness itself, which seems to depend on the coherent flow of information through time, might be impossible in a reality where causality was negotiable. The prohibition against faster-than-light travel might therefore represent more than just a speed limit. It might be a fundamental requirement for the existence of an ordered, comprehensible universe where conscious beings can emerge and contemplate their own existence. The cosmic speed limit preserves not just the logical structure of physics, but the very possibility of physics being comprehended by conscious minds. As we drift deeper into these profound mysteries, we begin to see that the relationship between faster-than-light travel and temporal paradoxes touches on some of the deepest questions in all of science and philosophy. What is the nature of time? Why does causality seem to flow in only one direction? How does the universe maintain its logical consistency across all scales of space and time? These questions don't have simple answers, but exploring them reveals the elegant architecture that underlies reality itself. The speed of light emerges not as an arbitrary constant, but as a fundamental organizing principle that shapes the structure of spacetime and preserves the coherent evolution of the cosmos. In the gentle quiet of this moment, as your thoughts wander among these cosmic mysteries, you're participating in one of humanity's most profound inquiries. The question of why we cannot travel faster than light leads us directly to the heart of existence itself, revealing the delicate balance of laws and principles that make our universe not just possible, but comprehensible. The prohibition against faster-than-light travel stands as a testament to the universe's commitment to logical consistency. Its insistence that reality remain coherent even in the face of our most ambitious dreams of cosmic exploration. It reminds us that some boundaries exist not to limit us, but to preserve the very foundations upon which all possibilities rest. The strange world of theoretical physics offers us a handful of exotic particles that might, in principle, travel faster than light. These hypothetical entities, called tachyons, would exist in a mirror image of our familiar reality, where faster means lower energy rather than higher energy. While normal particles require infinite energy to reach the speed of light, tachyons would require infinite energy to slow down to the speed of light. They would be forever trapped in the faster-than-light realm, just as we are forever trapped below it. The mathematics describing tachyons is elegant and internally consistent, but it leads to some deeply unsettling conclusions. If tachyons could carry information, they would transform into cosmic messengers capable of delivering news from the future to the past. Imagine receiving a tachyonic telegram that arrived yesterday warning you about an event that hasn't happened yet. The logical contradictions multiply like ripples in a temporal pond. Consider this scenario carefully. You're sitting in your laboratory on Earth and you decide to conduct an experiment involving tachyonic communication with a colleague on a distant space station. You send a tachyon beam carrying a simple message: press the red button. From your perspective, the message travels faster than light and arrives at the space station in the future. Your colleague receives it and, following your instructions, presses the red button. But now consider the perspective of an observer travelling at high speed relative to both Earth and the space station. Due to the relativity of simultaneity, this moving observer might see your colleague pressing the red button before you sent the message telling them to do so. From their reference frame, the effect has preceded the cause, creating a causal loop that seems to violate the logical structure of reality itself. The situation becomes even more paradoxical when we introduce the possibility of tachyonic replies. Imagine that after pressing the red button, your colleague immediately sends a tachyonic message back to you saying, "Button pressed successfully." This return message, travelling faster than light in the opposite direction, might reach you before you sent your original instruction. You could receive confirmation of an action that you haven't yet requested. Now, consider what happens if that return message says something different. What if it says, "Do not send the message. You receive this instruction from the future. Decide to follow it and never send the original message." But if you never send the original message, your colleague never receives it, never presses the button, and never sends the reply telling you not to send the message. The logical contradiction creates what physicists call the tachyonic anti-telephone paradox. These aren't just abstract mathematical puzzles, they represent genuine predictions of what would happen if faster-than-light particles could carry information. The relativistic framework that governs our universe makes these paradoxes inevitable whenever faster-than-light communication is introduced into the system. The universe seems to protect itself from such contradictions by simply not allowing tachyons to exist, or at least not allowing them to carry information. Experimental searches for tachyons have found no evidence of their existence. Every attempt to detect faster-than-light particles has yielded null results, suggesting that the universe has indeed prohibited their creation. This absence isn't just a failure of our detection methods, it appears to be a fundamental feature of reality itself. But the theoretical exploration of tachyons has revealed something profound about the relationship between information, causality, and the structure of spacetime. Even if tachyons existed, there might be built-in mechanisms that prevent them from creating paradoxes. Some theories suggest that tachyonic signals automatically adjust themselves to maintain causal consistency, becoming self-correcting messengers that preserve the logical flow of events. Other approaches propose that tachyon communication might be fundamentally ambiguous, making it impossible for observers to distinguish between emission and absorption of these faster-than-light particles. In this view, receiving a tachyon from the future would be indistinguishable from emitting a tachyon into the past, creating a symmetry that prevents the formation of causal loops. These proposed solutions remain highly speculative, and most physicists suspect that the simplest resolution is that tachyons simply don't exist. The universe appears to have chosen logical consistency over exotic possibilities, preferring a reality where cause and effect maintain their proper sequence over one where faster-than-light communication is possible. The story becomes even more intriguing when we consider quantum mechanics and its strange relationship with faster-than-light phenomena. At the quantum level, particles can become entangled, creating instantaneous correlations that seem to transcend the light speed barrier. When you measure the state of one entangled particle, you instantly know something about its partner, regardless of the distance separating them. This quantum entanglement initially appears to violate the prohibition against faster-than-light communication. The correlations between entangled particles are established instantaneously, suggesting that information can somehow leap across space without respecting the cosmic speed limit. Einstein famously called this spooky action at a distance, and it troubled him deeply because it seemed to contradict his insights about the fundamental structure of spacetime. But deeper investigation reveals that quantum entanglement, while genuinely instantaneous, cannot be used to transmit useful information faster than light. The quantum correlations are perfectly real, but they're also perfectly random from the perspective of any individual observer. You can't use entanglement to send a message because you can't control what message would be sent. Imagine you and your friend each have one particle from an entangled pair. When you measure your particle and find it spinning clockwise, you instantly know that your friend's particle is spinning counterclockwise. This correlation was established faster than light could travel between you, but you can't use this effect to communicate because you can't control which way your particle will be spinning when you measure it. The result is random, determined by the quantum mechanical wave function, collapse. Your friend, measuring their particle, sees equally random results. Only when you later compare your measurements through conventional, slower-than-light communication do you discover the correlations that quantum mechanics predicted. The instantaneous aspect of quantum entanglement never carries information that could be used to create causal paradoxes. This elegant resolution preserves both the reality of quantum mechanical effects and the prohibition against faster-than-light communication. The universe allows instantaneous correlations but prevents them from being used to transmit information that could disrupt causality. It's as if reality has found a way to have its quantum cake and eat its relativistic cake too. Recent developments in quantum computing have added new dimensions to this story. Quantum computers achieve their remarkable processing power by exploiting quantum superposition and entanglement, performing calculations that would be impossible for classical computers. Some interpretations suggest that these quantum computers are actually borrowing computational power from parallel universes, accessing vast resources through quantum mechanical effects. But even these exotic quantum phenomena respect the fundamental prohibition against faster-than-light information transfer. Quantum computers can process information in ways that seem to transcend classical limitations, but they cannot send messages to the past or communicate faster than light with distant locations. The quantum realm, for all its strangeness, still operates within the causal constraints that preserve the logical structure of spacetime. The geometric approach to understanding faster-than-light travel and temporal paradoxes reveals the deep mathematical beauty underlying these constraints. Spacetime diagrams provide a visual framework for understanding how causality operates across different reference frames. In these diagrams, the 45-degree light cone boundaries separate regions of spacetime based on their causal relationships. Events within your future light cone can potentially be influenced by your actions right now. Events within your past light cone could have influenced your current situation. Events outside both light cones are causally disconnected from your present moment, unable to affect or be affected by what you do right now. This geometric structure creates the causal architecture of the universe, ensuring that influences propagate in an orderly fashion through spacetime. Faster-than-light signals would violate this geometric structure, connecting events that should be causally disconnected. They would create pathways between regions of spacetime that the light cone structure declares should be isolated from each other. In doing so, they would undermine the very foundation upon which causal consistency rests. The mathematical elegance of this geometric approach reveals why the prohibition against faster-than-light travel isn't just an arbitrary speed limit. It emerges from the fundamental geometry of spacetime itself, from the mathematical relationships that define how space and time are woven together into a unified fabric. Violating the speed of light doesn't just break a rule, it breaks the geometric structure that makes coherent spacetime possible. These insights have profound implications for our understanding of the universe's architecture. Reality appears to be constructed in such a way that its own logical consistency is preserved at the deepest possible level. The prohibition against faster-than-light travel isn't imposed from outside. It emerges naturally from the mathematical relationships that define the structure of existence itself. As we drift deeper into these mysteries, we begin to see that the question of faster-than-light travel touches on fundamental issues in physics that extend far beyond simple velocity limits. The relationship between space and time, the nature of causality, the role of information in physical processes, all of these deep concepts are interconnected in ways that preserve the coherent structure of reality. The universe seems to have evolved or been designed in such a way that conscious observers can emerge and comprehend their surroundings without being overwhelmed by paradoxes and contradictions. The prohibition against faster-than-light travel may be just one aspect of a broader cosmic principle that ensures reality remains comprehensible to the minds that arise within it. In the gentle quiet of this moment, as your thoughts settle like cosmic dust after contemplating these profound mysteries, remember that you're participating in one of humanity's deepest inquiries into the nature of existence. The connection between faster-than-light travel and temporal paradoxes reveals the elegant constraints that shape our universe, the invisible boundaries that preserve the logical foundation upon which all of reality rests. The speed of light stands not as a barrier to our cosmic ambitions, but as a guardian of causality itself, ensuring that the universe remains a place where effects follow causes, where the future grows naturally from the past, and where conscious beings can contemplate their place in the grand scheme of existence without being lost in logical contradictions that would make comprehension impossible. These cosmic speed limits remind us that some boundaries exist not to frustrate our dreams, but to preserve the very foundations that make dreaming possible. In accepting these constraints, we discover not limitation, but liberation. Not the end of possibility, but the beginning of understanding what kinds of possibilities can actually exist in a logically coherent universe. The profound implications of faster-than-light travel extend into realms that challenge our most basic assumptions about the nature of reality itself. As we venture deeper into this cosmic puzzle, we encounter scenarios that seem to tear at the very fabric of logical thought, creating situations where the familiar sequence of cause and effect becomes hopelessly tangled. Consider the grandfather paradox in its most elegant and devastating form. Imagine you've somehow acquired the ability to send faster-than-light messages through space. In a moment of cosmic mischief, you decide to send a signal to a distant star system with instructions for an automated probe there to launch a projectile back toward Earth. Due to the relativistic effects we've explored, this projectile could arrive at Earth before you sent the original message, potentially striking you down before you ever conceived of sending the signal in the first place. The logical contradiction is breathtaking in its simplicity. If the projectile prevents you from sending the message, then the message is never sent, the projectile is never launched, and you remain unharmed and free to send the message that would trigger your own demise. It's a causal loop that eats its own tail, a logical snake that devours itself in an endless cycle of contradiction. But the universe seems to have anticipated such paradoxes and woven protections against them into the very mathematical structure of spacetime. The chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics conspire to prevent the formation of closed time-like curves, those pathways through spacetime that would allow effects to precede their causes. This protection might manifest in subtle ways that we're only beginning to understand. Quantum fluctuations in the vacuum of space might grow unstable whenever spacetime approaches a configuration that would permit time travel. The energy required to create such configurations might always exceed what's physically possible, or the very attempt to construct a temporal paradox might trigger feedback effects that automatically prevent its completion. The mathematics of general relativity reveal additional layers of protection against causal violations. When physicists calculate the energy requirements for exotic spacetime manipulations like wormhole creation or Alcubierre drive construction, they consistently find that impossible amounts of exotic matter would be needed. The universe seems to price temporal paradoxes out of the market, making them so expensive in terms of energy and exotic matter that they become effectively impossible to achieve. These energy barriers aren't arbitrary obstacles but emerge naturally from the equations that govern spacetime geometry. Einstein's field equations relate the curvature of spacetime to the distribution of matter and energy within it. To create the kinds of extreme curvature that would permit faster than light travel or time travel, you would need forms of matter and energy that may simply not exist in our universe. Exotic matter with negative energy density represents one such requirement. This hypothetical substance would have the peculiar property of creating gravitational repulsion rather than attraction. While quantum field theory allows for small amounts of negative energy under very specific conditions, scaling up these effects to macroscopic levels appears to violate fundamental energy conditions that govern the behavior of matter and fields. The Casimir effect demonstrates that negative energy can exist on microscopic scales, where quantum fluctuations in the vacuum create measurable forces between closely spaced conducting plates. But attempts to amplify these effects to the levels needed for faster than light travel run into what physicists call the quantum inequality, a fundamental limit on how much negative energy can be concentrated in any given region of space. These quantum constraints suggest that the universe has built-in mechanisms that prevent the large-scale manipulation of spacetime geometry required for exotic propulsion systems. Even if we could theoretically design devices that would enable faster-than-light travel, quantum mechanics might make them impossible to construct or operate in practice. The relationship between faster-than-light travel and temporal paradoxes becomes even more intricate when we consider the role of information in physical processes. Modern physics has revealed that information is not just an abstract concept, but a fundamental feature of reality that obeys its own conservation laws and limitations. The no-communication theorem in quantum mechanics demonstrates that quantum entanglement, despite creating instantaneous correlations between distant particles, cannot be used to transmit information faster than light. This theorem protects causality at the quantum level, ensuring that the strange properties of quantum mechanics don't lead to violations of relativistic constraints. Similarly, the holographic principle suggests that the information content of any region of space is limited by the area of its boundary rather than its volume. This principle, which emerges from studies of black hole thermodynamics, might impose fundamental limits on how much information can be processed or transmitted by any physical system, potentially constraining the kinds of exotic matter distributions needed for faster than light travel. These information-theoretic constraints point toward a deeper unity underlying the laws of physics. The prohibition against faster than light travel isn't just about velocity limits or energy requirements. It's about preserving the fundamental relationship between information, causality, and the structure of spacetime itself. As we explore these cosmic boundaries, we begin to appreciate the elegant interconnectedness of physical law. Every constraint reinforces every other constraint, creating a web of logical consistency that extends from the quantum realm to the cosmic scale. The universe appears to be constructed as a self-consistent mathematical structure, where violations of one principle automatically trigger protections from other principles. This multi-layered protection system suggests that the prohibition against faster than light travel represents more than just a technical challenge. It reflects a fundamental aspect of how reality is organized, a cosmic commitment to maintaining logical coherence across all scales of space and time. The search for loopholes in these cosmic speed limits has led physicists to explore increasingly exotic possibilities. Some have proposed that higher dimensional theories might allow for faster than light travel through extra dimensions that we cannot directly perceive. Others have suggested that the fundamental constants of nature might vary across space and time, creating regions where the speed of light itself is different. But each of these speculative possibilities brings its own challenges and potential paradoxes. Higher dimensional theories require enormous energies to access the extra dimensions, energies that may exceed what's available in our universe. Variable speed of light theories must carefully preserve the causal structure of spacetime to avoid creating new forms of temporal paradox. The more we probe the boundaries of what's possible, the more we discover that the universe has anticipated our every attempt to circumvent its fundamental limitations. Each proposed loophole seems to close itself through mechanisms we're only beginning to understand, as if reality has an immune system that protects it against logical contradictions. This cosmic immune system might be related to the anthropic principle, the observation that the universe appears to be fine-tuned for the existence of conscious observers. If temporal paradoxes were common, if faster than light travel were easily achievable, the resulting causal chaos might prevent the formation of stable structures capable of supporting life and consciousness. The prohibition against faster than light travel might therefore be connected to the very possibility of consciousness existing in the universe. The cosmic speed limit doesn't just preserve abstract principles of causality, it preserves the conditions necessary for minds like ours to emerge and contemplate their place in the cosmic order. This connection between velocity limits and consciousness raises profound questions about the nature of observation and measurement in physics. Quantum mechanics suggests that conscious observation plays a fundamental role in determining the outcomes of quantum events. If consciousness is indeed necessary for the collapse of quantum wave functions, then the existence of conscious observers might be required for the universe to maintain its classical appearance. In such a framework, the prohibition against faster than light travel might represent a kind of cosmic quality control system, ensuring that the universe remains comprehensible to the conscious minds that arise within it. Faster than light travel would create causal loops that could undermine the coherent flow of information through time, potentially making it impossible for consciousness to maintain a consistent understanding of reality. The relationship between faster than light travel and temporal paradoxes thus connects to some of the deepest mysteries in physics and philosophy. The nature of time itself, the role of consciousness in physical processes, the question of why the universe is comprehensible to minds that evolved within it. All of these profound issues are intertwined with the seemingly simple question of whether we can travel faster than light. Recent developments in theoretical physics have added new dimensions to these considerations. String theory, with its extra dimensions and exotic mathematical structures, offers potential pathways around some of the traditional barriers to faster than light travel. But string theory also introduces new forms of constraint and protection, ensuring that causality remains intact even in higher dimensional frameworks. Loop quantum gravity, another approach to unifying quantum mechanics and general relativity, suggests that spacetime itself might have a discrete, granular structure at the smallest scales. This quantum foam might impose fundamental limits on how precisely we can manipulate spacetime geometry, potentially preventing the formation of exotic configurations that would permit faster than light travel. These cutting-edge theories reveal that the prohibition against faster than light travel isn't just a consequence of Einstein's relatively simple, special and general theories of relativity. It appears to be a robust feature of physics that persists even in the most exotic theoretical frameworks we can construct. The more we learn about the fundamental structure of reality, the more we discover that the universe has multiple, redundant systems for protecting causality and preventing temporal paradoxes. It's as if reality has evolved sophisticated defenses against logical contradiction, ensuring that the cosmos remains a place where cause and effect maintain their proper relationship. This protection of causality might be related to the deep mathematical structures that underlie physical law. The universe appears to be governed by mathematical relationships of extraordinary beauty and consistency. These relationships might inherently prohibit configurations that would lead to logical contradictions, making the prohibition against faster-than-light travel a natural consequence of the mathematical harmony that pervades reality. As we contemplate these cosmic mysteries in the gentle quiet of this moment, we're reminded that the question of faster-than-light travel opens doorways to some of the most profound issues in all of science. The relationship between space and time, the nature of causality, the role of consciousness in physical processes, the mathematical foundations of reality itself. All of these deep concepts converge in the seemingly simple question of whether we can exceed the cosmic speed limit. The universe's answer appears to be a resounding no, not because it wishes to limit our cosmic ambitions, but because preserving the logical consistency of reality requires certain fundamental constraints. These constraints don't represent failures of physics or limitations on human potential. They represent the necessary conditions for a universe where conscious beings can emerge and contemplate their place in the grand scheme of existence. The speed of light stands as more than just a velocity limit. It serves as a guardian of causality, a protector of logical consistency, a cosmic constant that ensures the universe remains comprehensible to the minds that arise within it. In accepting this limitation, we don't surrender our dreams of cosmic exploration. We gain a deeper appreciation for the elegant architecture that makes such dreams possible in the first place. The prohibition against faster-than-light travel reminds us that some boundaries exist, not to constrain us, but to preserve the very foundations upon which all possibilities rest. In a universe where causality was negotiable, where effects could routinely precede their causes, the stable conditions necessary for the emergence of complexity, life, and consciousness might never arise. Our cosmic speed limit thus represents not a cosmic conspiracy against human ambition, but a fundamental requirement for the existence of an ordered, comprehensible reality where beings like ourselves can emerge and wonder about the nature of existence itself. The universe has chosen logical consistency over exotic possibilities, and in doing so has created the conditions that make our very questioning possible. As we drift deeper into this cosmic meditation on the nature of velocity and causality, we encounter perhaps the most elegant and unsettling realization of all. The universe doesn't just prohibit faster than light travel through arbitrary rules or impossible energy requirements. It weaves this prohibition into the very mathematical poetry that describes existence itself. Consider for a moment the profound implications of what we call spacetime intervals. These mathematical constructs represent the true distances between events in our four-dimensional universe, distances that remain constant regardless of how different observers might measure space and time separately. When you calculate the spacetime interval between any two events connected by slower than light signals, you get a positive number. This positive interval ensures that all observers will agree on the causal ordering of these events. But something remarkable happens when faster than light signals enter this mathematical framework. The spacetime intervals become negative, creating what physicists call space-like separations. These negative intervals are like mathematical warning signs, cosmic red flags that indicate we've entered territory where the normal rules of causality begin to break down. It's as if the universe has embedded a kind of mathematical immune system into its deepest structures, automatically flagging any configuration that might threaten the logical consistency of reality. The mathematics itself rebels against faster-than-light travel, not through external prohibition, but through internal contradiction. This mathematical resistance extends to every level of physical theory. In quantum field theory, the equations that describe the creation and annihilation of particles contain built-in constraints that prevent faster-than-light propagation of information. The mathematical structures naturally enforce what physicists call microscopic causality, ensuring that quantum events maintain proper causal ordering even at the smallest scales. In thermodynamics, the laws governing heat and entropy create their own barriers to faster-than-light travel. The exotic matter configurations required for such travel would violate fundamental energy conditions, creating thermodynamic impossibilities that the universe seems constitutionally unable to permit. It's as if the mathematical fabric of reality has an allergic reaction to causal violations. Even in the realm of pure mathematics, divorced from physical considerations, we find structures that seem to echo these causal constraints. The geometric properties of hyperbolic space, the topology of complex manifolds, the algebraic relationships between symmetry groups, all of these abstract mathematical concepts contain echoes of the causal structure that governs our physical universe. This deep mathematical consistency suggests something profound about the nature of reality itself. Perhaps the universe isn't just governed by mathematical laws, but is itself a kind of mathematical structure, a vast equation that maintains its own internal consistency through mechanisms we're only beginning to glimpse. The ancient Pythagoreans believed that number was the essence of all things, that mathematical relationships formed the hidden architecture of reality. Modern physics has vindicated this intuition in ways they could never have imagined. The prohibition against faster-than-light travel emerges not as an arbitrary constraint imposed from outside reality, but as an inevitable consequence of the mathematical harmony that underlies existence itself. But our journey through these cosmic mysteries reveals something even more remarkable about the relationship between consciousness and the fundamental structure of space-time. We are not merely passive observers of these mathematical relationships, but active participants in a universe that seems designed to be comprehensible to minds like ours. The fact that we can understand these deep connections between velocity, causality, and temporal paradoxes suggests something profound about our place in the cosmic order. Consciousness has emerged in a universe structured in such a way that it can comprehend its own foundations, can recognize the mathematical beauty that governs its operation, can appreciate the elegant constraints that preserve its logical consistency. This capacity for cosmic understanding might be more than just a fortunate accident. Some physicists and philosophers have suggested that consciousness plays a fundamental role in the structure of reality itself, that the universe requires conscious observers not just to measure quantum events, but to maintain the coherent flow of information through time. In this view, the prohibition against faster-than-light travel might be connected to the very existence of consciousness in the universe. Faster-than-light travel would create causal loops that could disrupt the orderly flow of information through time, potentially making it impossible for conscious minds to maintain a coherent understanding of their surroundings. The universe might therefore protect causality not just as an abstract mathematical principle, but as a prerequisite for the existence of conscious observers capable of appreciating its mathematical beauty. The cosmic speed limit serves as a guardian not just of logical consistency, but of the very possibility of minds arising that can contemplate these deep questions. This connection between velocity limits and consciousness raises fascinating questions about the nature of time itself. We experience time as flowing from past to future, creating what physicists call the arrow of time. But the fundamental equations of physics are largely time-symmetric, working equally well whether time flows forward or backward. The prohibition against faster-than-light travel might be connected to this mysterious arrow of time. Perhaps causality provides the mechanism that breaks the time symmetry of fundamental physics, creating the directed flow of time that conscious beings experience. In this view, faster-than-light travel wouldn't just violate causality, it would threaten the very foundation of temporal experience itself. Recent developments in quantum mechanics have added new layers to this mystery. The phenomenon of quantum decoherence shows how quantum systems interact with their environment in ways that create the appearance of classical reality from underlying quantum possibilities. This decoherence process is intimately connected to the flow of information through time and might provide the mechanism that enforces the arrow of time. If faster-than-light travel could disrupt this delicate quantum decoherence process, it might not just create temporal paradoxes, but could unravel the very mechanisms that create our classical experience of reality. The prohibition against exceeding the cosmic speed limit might therefore protect not just causality, but the entire classical world that emerges from quantum foundations. These insights reveal that the relationship between faster-than-light travel and temporal paradoxes touches on the deepest mysteries of existence. The nature of time, the role of consciousness, the emergence of classical reality from quantum foundations, the mathematical structure of physical law, all of these profound concepts are interconnected in ways that preserve the coherent structure of the universe we inhabit. The cosmic speed limit emerges not as an arbitrary barrier, but as a fundamental organizing principle that shapes every aspect of reality from the quantum scale to the cosmic scale. It ensures that information flows in coherent patterns through spacetime, that conscious observers can emerge and maintain stable understanding of their surroundings, that the mathematical beauty underlying physics remains accessible to minds capable of appreciating it. As we rest in the gentle contemplation of these cosmic mysteries, we begin to see that the prohibition against faster-than-light travel represents something far more profound than a mere technical limitation. It reflects the universe's deep commitment to maintaining the conditions necessary for consciousness, complexity, and comprehension. The speed of light stands as a cosmic constant, not just in the physical sense, but in the deeper sense of preserving the constants of logical thought, causal reasoning, and meaningful experience. It protects the foundations upon which all of our understanding rests, ensuring that the universe remains a place where questions can be asked and answers can be found. In accepting this cosmic speed limit, we don't surrender our dreams of exploring the vast reaches of space and time. Instead, we gain a deeper appreciation for the elegant architecture that makes such dreams meaningful. We discover that some boundaries exist not to limit possibility, but to preserve the very conditions that make possibility comprehensible. The universe has chosen logical consistency over exotic travel options, and in doing so has created a reality where conscious beings can emerge and contemplate their place in the grand scheme of existence. The prohibition against faster-than-light travel thus becomes not a cosmic disappointment, but a cosmic gift, preserving the coherent structure of spacetime that allows minds like ours to wonder about the nature of reality itself. As your thoughts begin to settle like cosmic dust in the gentle darkness, remember that you've been contemplating one of the most elegant and profound connections in all of physics. The relationship between velocity and causality reveals the deep mathematical harmony that underlies existence, the invisible architecture that preserves meaning and comprehension in a universe vast beyond imagination. The cosmic speed limit reminds us that we live in a reality governed not by arbitrary rules, but by mathematical relationships of extraordinary beauty and consistency. These relationships don't constrain us but liberate us, creating the stable foundation upon which all understanding, all wonder, and all conscious experience ultimately rests. In the quiet space between one heartbeat and the next, you touch something eternal about the nature of existence itself. The same mathematical principles that prohibit faster-than-light travel also ensure that this moment of contemplation is possible, that consciousness can arise in a universe structured to be comprehensible to the minds that emerge within it. The prohibition against exceeding the cosmic speed limit thus becomes a celebration of the universe's commitment to logical beauty, to causal consistency, to the preservation of meaning itself. It reminds us that some of the most profound truths about reality emerge not from what's possible, but from understanding why certain impossibilities are necessary for the coherent structure of existence. Rest now in this cosmic understanding, knowing that the same elegant constraints that prevent us from travelling faster than light also create the stable foundation upon which all knowledge, all wonder, and all conscious appreciation of the universe's mathematical beauty ultimately depends. The cosmic speed limit stands not as a barrier to transcendence, but as the very condition that makes transcendent understanding possible. The deeper we venture into this cosmic labyrinth, the more we discover that the universe has woven its protection against temporal paradoxes into every conceivable corner of reality. It's as if existence itself has developed an immune system against logical contradiction, deploying multiple layers of defense that operate across all scales of space and time. Consider the extraordinary precision with which these protections operate. When physicists calculate the exact conditions required for creating traversable wormholes, those hypothetical tunnels through space-time that might serve as shortcuts across the cosmos, they consistently find that the energy requirements exceed what appears to be physically possible. Not by a small margin, mind you, but by factors so enormous they beggar comprehension. To stabilize even the tiniest wormhole, one barely large enough for a single photon to pass through, would require exotic matter equivalent to the mass of entire star systems. And this exotic matter wouldn't just be difficult to obtain, it would need to possess properties that may fundamentally violate the energy conditions that govern how matter and fields behave throughout the universe. The quantum field fluctuations that fill what we think of as empty space impose their own subtle constraints on any attempt to manipulate spacetime geometry. These fluctuations, arising from the inherent uncertainty that governs the quantum realm, create what physicists call the quantum stress energy tensor. This mathematical object describes how quantum effects influence the curvature of spacetime, and it appears to automatically resist any configuration that might permit faster than light travel. It's as if the quantum vacuum itself serves as a kind of cosmic quality control system, monitoring spacetime for potential violations of causality and automatically generating resistance whenever such violations threaten to emerge. The more severely you attempt to curve spacetime, the more strongly these quantum effects push back, creating an escalating battle between your exotic matter and the universe's quantum defenses. But perhaps most remarkably, these quantum protections operate with surgical precision. They don't prevent all forms of spacetime curvature, only those specific configurations that would lead to causal violations. Black holes, for instance, create extreme curvature without generating closed time-like curves, at least not in their exterior regions. The universe seems capable of distinguishing between helpful curvature that organizes matter and energy and dangerous curvature that threatens causality. This precision suggests something profound about the mathematical structure underlying physical law. The equations that govern spacetime geometry don't just describe how matter curves space and time. They embed within themselves a kind of logical consistency checker that automatically flags and prevents configurations that would lead to paradoxes. Recent theoretical work has revealed even more subtle protections against temporal paradoxes. The phenomenon of chronology protection, first proposed by Stephen Hawking, might operate through quantum effects that become unstable whenever spacetime approaches a configuration that would permit time travel. As you get closer and closer to creating a closed time-like curve, quantum fluctuations grow larger and larger, ultimately becoming so violent that they destroy the exotic matter configuration before it can complete the formation of a temporal loop. These quantum fluctuations don't arise randomly, but appear to be triggered specifically by the approach to causal violation. It's as if the universe has developed an early warning system that detects potential threats to causality and mobilizes quantum defenses before those threats can fully materialize. The mathematical elegance of this protection mechanism is breathtaking. The same quantum field theory that describes the behavior of particles and forces also contains within itself the seeds of its own causal protection. The theory doesn't need external enforcement mechanisms or arbitrary prohibitions. It naturally generates its own safeguards against logical contradiction. This self-protecting quality of physical law extends beyond just spacetime geometry into the realm of information theory. The fundamental limits on information processing and transmission appear to be intimately connected to the prohibition against faster-than-light travel. The holographic principle, emerging from studies of black hole thermodynamics, suggests that the information content of any region of space is limited by the area of its boundary rather than its volume. This holographic bound might impose fundamental constraints on how much information can be manipulated or transmitted by any physical system, potentially limiting the kinds of exotic matter distributions needed for faster-than-light travel. If information is indeed fundamental to the structure of reality, then the limits on information processing might automatically enforce the limits on causal manipulation. Consider the profound implications of this connection between information and causality. Every faster-than-light signal would need to carry information from one location to another, but the holographic principle suggests that there are fundamental limits on how much information can be concentrated in any given region of spacetime. These limits might make it impossible to create the precisely controlled exotic matter distributions required for causal violations. The relationship between information and energy adds another layer of protection. Landauer's principle, established in the foundations of computational thermodynamics, shows that erasing information requires energy. If faster-than-light travel inevitably leads to causal loops where information must be erased or created from nothing, then thermodynamic constraints might automatically prevent such loops from forming. Imagine trying to send a message to your own past. The information in that message would need to exist in a closed loop, with no ultimate origin or destination. But thermodynamic laws governing information processing might prohibit such self-existing information loops, creating yet another barrier against temporal paradoxes. These information-theoretic protections operate at a more fundamental level than even quantum mechanics or general relativity. They suggest that the prohibition against faster-than-light travel might be rooted in the deepest logical structures that govern how information can exist and flow through any conceivable reality. The search for loopholes in these cosmic protections has led theoretical physicists to explore increasingly exotic possibilities. Some have proposed that higher dimensional theories might allow for faster-than-light travel through extra dimensions that we cannot directly perceive. In these theories, our familiar three-dimensional space might be embedded in a higher dimensional bulk, and it might be possible to take shortcuts through this bulk that would appear as faster-than-light travel from our limited three-dimensional perspective. But even these higher dimensional theories come equipped with their own sophisticated protection mechanisms. The energy required to access the extra dimensions typically exceeds what's available in our universe by enormous factors. The curvature of the higher dimensional space might automatically prevent the formation of shortcuts that would violate causality in our three-dimensional world. Moreover, higher dimensional theories often contain their own versions of the speed of light limit, cosmic speed limits that operate in the full higher dimensional space and prevent faster-than-light travel, even when additional dimensions are available. The universe seems to have anticipated even our most exotic theoretical escape routes and sealed them off with mathematical precision. String theory, perhaps the most ambitious attempt to unify all of physics, provides another fascinating example of how causal protection mechanisms operate at the deepest levels of theoretical physics. In string theory, the fundamental building blocks of reality are not point particles, but tiny vibrating strings existing in higher dimensional space. These strings are governed by mathematical relationships of extraordinary complexity and beauty. But embedded within the mathematics of string theory are constraints that automatically prevent faster-than-light travel. The vibrational modes of strings that would correspond to faster-than-light particles turn out to be unstable, decaying rapidly into more conventional, slower-than-light states. The theory naturally eliminates its own potential for causal violation through internal mathematical consistency requirements. Even more remarkably, string theory suggests that the dimensionality of spacetime itself might be determined by consistency requirements related to causal protection. The theory works consistently only in specific numbers of dimensions, and these preferred dimensions appear to be precisely those that maintain stable causal structure while allowing for the rich physics we observe in our universe. This connection between dimensional structure and causal protection suggests that the very fabric of spacetime might be shaped by the requirement that reality remain logically consistent. The number of spatial dimensions, the flow of time, the relationship between matter and geometry, all of these fundamental features of our universe might be determined by the deeper requirement that causality be preserved. Loop quantum gravity, another approach to unifying quantum mechanics and general relativity, reveals yet another layer of causal protection operating at the smallest possible scales. This theory suggests that spacetime itself has a discrete, granular structure at distances comparable to the Planck length, roughly 10 to the power of negative 35 meters. At these incredibly tiny scales, the smooth geometry of classical spacetime gives way to a foamy, fluctuating quantum structure, where the usual concepts of distance and duration become fuzzy and uncertain. This quantum foam might impose fundamental limits on how precisely we can manipulate spacetime geometry, potentially preventing the formation of the exotic configurations that would permit faster-than-light travel. The discrete structure of quantum spacetime creates natural cutoffs in the mathematical descriptions of extreme curvature. Just as digital images have limited resolution determined by their pixel size, quantum spacetime might have limited geometric resolution determined by the Planck scale. These resolution limits might automatically prevent the formation of the infinitely sharp features that would be required for some forms of faster-than-light travel. But perhaps most intriguingly, loop quantum gravity suggests that time itself might have a discrete granular structure at the smallest scales. Instead of flowing smoothly like a river, time might tick forward in discrete quantum steps, each step corresponding to 1 unit of Planck time, roughly 10 to the power of negative 43 seconds. This discretization of time creates natural barriers against certain types of temporal paradox. If time really does have a granular structure, then it might be impossible to create the precisely controlled temporal loops required for sending information to the past. The discrete nature of time would introduce unavoidable uncertainties that could prevent the formation of perfectly closed causal loops. These quantum gravity insights reveal that the protection against temporal paradoxes might extend all the way down to the most fundamental level of spacetime structure. Even at scales where quantum effects dominate and classical concepts break down, the universe maintains its commitment to causal consistency through mechanisms we're only beginning to understand. The remarkable consistency of these protection mechanisms across all scales and all theoretical frameworks suggests something profound about the nature of physical law itself. From classical general relativity to quantum field theory, from thermodynamics to information theory, from string theory to loop quantum gravity, every approach to understanding the deepest levels of reality reveals the same fundamental commitment to preserving causality. This isn't just a coincidence or a conspiracy among physicists to maintain consistent theories. It appears to reflect something essential about the mathematical structures that can support coherent, self-consistent realities. The prohibition against faster-than-light travel emerges not as an arbitrary constraint, but as a necessary feature of any universe capable of maintaining logical coherence across space and time. Recent developments in the foundations of quantum mechanics have added even more layers to this story. The phenomenon of quantum error correction, discovered in the context of quantum computing, reveals how quantum systems can maintain coherent information even in the presence of noise and interference. These quantum error correction mechanisms might operate in the structure of spacetime itself, automatically correcting any distortions that might threaten causal consistency. If spacetime really does have quantum error correction mechanisms built into its fundamental structure, then attempts to create faster-than-light travel or time travel might trigger automatic correction processes that restore normal causal ordering. The universe might literally heal itself from causal wounds using quantum error correction to maintain the integrity of the timeline. The holographic principle adds yet another dimension to these protective mechanisms. If the information content of any region of space is encoded on its boundary, then the interior of that region might not have independent degrees of freedom that could be manipulated to create causal violations. The holographic encoding might automatically prevent the formation of exotic matter distributions that would threaten causality. This holographic protection would operate through the fundamental relationship between information and geometry. Any attempt to create the exotic curvature required for faster-than-light travel would need to be consistent with the holographic encoding of information on the boundary of the region. But this encoding might impose constraints that make such exotic curvature impossible to achieve. As we drift deeper into these interconnected mysteries, we begin to see that the prohibition against faster-than-light travel represents far more than just a speed limit. It reflects the universe's deep mathematical commitment to maintaining logical consistency across all possible scales and all possible theoretical frameworks. The cosmos appears to be constructed as a self-consistent mathematical structure where every level of description reinforces every other level in preserving causal order. From the largest scales of cosmological expansion to the smallest scales of quantum foam, From the most classical descriptions of matter and energy to the most exotic theoretical possibilities, reality maintains its commitment to ensuring that effects follow causes in a coherent, comprehensible sequence. This mathematical consistency might be related to what some physicists call the principle of cosmic censorship, the idea that the universe protects observers from encountering physical situations that would be incomprehensible or paradoxical. Just as event horizons around black holes prevent us from directly observing the singularities at their centers, the prohibition against faster-than-light travel might protect us from encountering the logical contradictions that would arise from causal violations. But unlike event horizons, which hide singularities from view, the protection against faster-than-light travel operates by preventing the paradoxical situations from arising in the first place. The universe doesn't just hide its contradictions, it actively prevents them from forming through multiple layers of mathematical and physical constraints. This active protection of logical consistency suggests something remarkable about the relationship between mathematics and reality. Perhaps the universe isn't just described by mathematics, but is itself a kind of mathematical structure, one that maintains its own internal consistency through mechanisms embedded in its deepest foundations. The prohibition against faster-than-light travel thus becomes a window into the fundamental nature of existence itself. It reveals a cosmos committed not just to physical consistency, but to logical coherence, not just to the preservation of energy and momentum, but to the preservation of meaning and comprehensibility themselves. As you rest there in the gentle darkness, your thoughts settling like stardust after contemplating these profound mysteries, remember that you're touching something essential about the architecture of reality. The same mathematical principles that prevent faster-than-light travel also ensure that this moment of contemplation is possible, that consciousness can arise in a universe structured to be comprehensible to the minds that emerge within it. The cosmic speed limit stands not as a barrier to understanding, but as a foundation for understanding, preserving the causal structure that allows questions to be asked and answers to be found. In accepting this limit, we don't surrender our cosmic ambitions, but gain insight into the elegant mathematical poetry that underlies all existence. The universe has chosen logical beauty over exotic possibilities, and in doing so has created the conditions that make beauty itself recognizable to conscious minds. The prohibition against exceeding the speed of light thus becomes not a cosmic disappointment, but a cosmic gift, preserving the coherent structure of spacetime that allows wonder itself to flourish in the vast garden of existence. The universe's protection against temporal paradoxes operates with such exquisite precision that it seems almost conscious in its vigilance. Every mathematical framework we've developed to describe reality contains within itself not just the rules that govern how things work, but automatic safeguards that prevent those rules from being used to create logical contradictions. Consider the beautiful symmetry of this protection. The same equations that describe how massive objects curve spacetime also contain built-in resistance to the kinds of extreme curvature that would permit closed time like curves. It's as if the mathematics of general relativity has developed an immune response to its own potential for paradox creation. When theoretical physicists first discovered solutions to Einstein's field equations that seemed to allow time travel, they also discovered that these solutions required exotic matter with properties so strange they bordered on the impossible. Negative energy densities, matter that falls upward instead of downward, substances that would violate every energy condition we've ever observed in nature. The universe doesn't just make faster-than-light travel difficult, it makes it require ingredients that appear to be fundamentally unavailable in our reality. It's like finding a recipe for temporal manipulation only to discover that the required ingredients exist nowhere in the cosmic pantry. But the protection runs even deeper than missing ingredients. Recent theoretical work has revealed that even if we could somehow obtain the exotic matter needed for faster than light travel, the act of assembling it into the required configurations would likely trigger quantum effects that would destroy the system before it could operate. Imagine trying to build a house of cards in a hurricane. The more delicately balanced your structure becomes, the more sensitive it grows to any disturbance. The exotic matter configurations needed for faster than light travel appear to be similarly fragile, becoming increasingly unstable as they approach the precise arrangements that would permit causal violations. This quantum instability isn't random chaos, but appears to be specifically triggered by approaches to causal violation. The closer you get to creating a closed time-like curve, the more violent the quantum fluctuations become, as if the universe is deploying increasingly desperate measures to prevent the formation of temporal paradoxes. Stephen Hawking captured this insight in his chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel through mechanisms we're only beginning to understand. The universe might not need external enforcement of its causal rules because those rules enforce themselves through the very mathematical structures that define reality. The elegance of this self-protection extends into realms of physics we rarely consider in everyday life. Thermodynamics, the science of heat and energy flow, creates its own barriers to faster than light travel through the fundamental relationships between energy, entropy, and information. The second law of thermodynamics tells us that entropy, roughly speaking, the amount of disorder in a system, tends to increase over time. This law creates an arrow of time, a preferred direction for the evolution of physical systems. Faster than light travel, by enabling effects to precede their causes, would threaten this fundamental directionality of thermodynamic processes. Consider what would happen if you could send energy backward in time. You could create perpetual motion machines, violating the conservation of energy by borrowing power from your own future. You could reverse the increase of entropy, turning scrambled eggs back into whole ones, making hot coffee spontaneously separate into hot water and cold grounds. These thermodynamic impossibilities suggest that the prohibition against faster than light travel might be enforced not just by the geometry of spacetime, but by the fundamental laws governing energy and information flow. The universe protects causality through multiple, overlapping mechanisms that reinforce each other across all scales of physical description. The relationship between information and causality reveals perhaps the most profound layer of this protection. Modern physics has discovered that information isn't just something we use to describe reality. It appears to be a fundamental feature of reality itself, subject to its own conservation laws and processing limits. The holographic principle, emerging from studies of black holes and quantum gravity, suggests that all the information contained within any volume of space can be encoded on the boundary of that volume. This principle implies fundamental limits on information density that might automatically prevent the formation of the exotic matter configurations needed for faster than light travel. If you can't concentrate enough information in a small enough region to precisely control the required exotic matter distributions, then faster than light travel becomes impossible, not through energy barriers, but through information processing limitations. The universe might protect causality by limiting how much control we can exercise over the fundamental structure of spacetime. Recent developments in quantum computing have added fascinating new dimensions to this story. Quantum computers achieve their remarkable capabilities by exploiting quantum superposition and entanglement, performing calculations that would be impossible for classical computers. But even these exotic quantum effects respect the fundamental prohibition against faster than light information transfer. Quantum entanglement creates instantaneous correlations between particles separated by arbitrary distances, but these correlations cannot be used to transmit useful information faster than light. the quantum realm, for all its strangeness, still operates within the causal constraints that preserve the logical structure of spacetime. This quantum respect for causality suggests that the prohibition against faster-than-light travel extends all the way down to the most fundamental level of physical description. Even in the weird world of quantum mechanics, where particles can be in multiple states simultaneously and measurement outcomes seem to depend on the act of observation, the universe maintains its commitment to preserving causal order. The no-communication theorem in quantum mechanics provides mathematical proof that quantum entanglement cannot be used for faster-than-light communication, regardless of how cleverly we might try to exploit quantum effects. This theorem represents a fundamental limit built into the mathematical structure of quantum theory itself. But the protection against causal violations in the quantum realm operates through mechanisms even more subtle than explicit no-communication theorems. Quantum decoherence, the process by which quantum systems lose their quantum properties through interaction with their environment, appears to be intimately connected to the flow of information through time. This decoherence process might serve as a kind of quantum quality control system, ensuring that information flows in coherent patterns through spacetime. Attempts to disrupt this flow through faster-than-light signaling might trigger decoherence effects that automatically restore normal causal ordering. The precision with which these quantum protection mechanisms operate suggests something remarkable about the relationship between consciousness and physical law. We are conscious beings living in a universe that seems structured to remain comprehensible to conscious observers, even as it prohibits the kinds of exotic phenomena that would make such comprehension impossible. Consider the profound implications of this observation. In a universe where faster-than-light travel were common, where temporal paradoxes occurred regularly, where effects routinely preceded their causes, it might be impossible for stable patterns of information processing to emerge and persist. The delicate chains of causation that allow complex structures like brains to form and function might be constantly disrupted by temporal interference. The prohibition against faster-than-light travel might therefore be connected not just to abstract principles of logical consistency, but to the very possibility of consciousness existing in the universe. The cosmic speed limit doesn't just preserve causality, it preserves the conditions necessary for minds like ours to emerge and contemplate their place in the cosmic order. This connection between velocity limits and consciousness raises fascinating questions about the role of observation in physical processes. Quantum mechanics suggests that conscious measurement plays a fundamental role in determining the outcomes of quantum events. If consciousness is indeed necessary for the collapse of quantum wave functions, then the existence of conscious observers might be required for the universe to maintain its classical appearance. Recent theoretical work has explored the possibility that consciousness itself might serve as a kind of cosmic quality control system, maintaining the coherent flow of information through spacetime through the act of observation and measurement. In this view, conscious beings don't just observe the universe, they participate in creating the classical reality that emerges from quantum possibilities. If this participatory view of consciousness is correct, then the prohibition against faster-than-light travel might represent a fundamental requirement for the existence of conscious observers. Faster-than-light signals could disrupt the delicate quantum processes that allow consciousness to collapse wave functions and create classical reality from quantum potential. The universe might therefore protect causality not just as an abstract mathematical principle, but as a prerequisite for its own comprehensibility. The cosmic speed limit serves as a guardian not just of logical consistency, but of the very possibility of logic being applied by conscious minds that arise within the cosmic framework. These insights reveal that the relationship between faster-than-light travel and temporal paradoxes connects to some of the deepest mysteries in all of science and philosophy. The nature of consciousness, the emergence of classical reality from quantum foundations, the role of information in physical processes, the mathematical structure of physical law, all of these profound concepts are interconnected in ways that preserve the coherent structure of existence. The more we probe these connections, the more we discover that the universe appears to be constructed as an integrated whole, where every aspect reinforces every other aspect in maintaining logical consistency. The prohibition against faster-than-light travel isn't an isolated constraint, but part of a vast web of interconnected principles that ensure reality remains comprehensible to the conscious minds that emerge within it. As we drift deeper into contemplation of these cosmic mysteries, we begin to appreciate the extraordinary elegance of the universe's architecture. Every law of physics, every mathematical relationship, every quantum mechanical effect seems to work together in preserving the conditions necessary for conscious beings to exist and wonder about their place in the grand scheme of existence. The cosmic speed limit emerges not as an arbitrary barrier, but as a fundamental organizing principle that shapes every aspect of reality from the quantum scale to the cosmological scale. It ensures that information flows coherently through spacetime, that conscious observers can emerge and maintain stable understanding of their surroundings, that the mathematical beauty underlying physics remains accessible to minds capable of appreciating it. In the gentle quiet of this moment, as your thoughts settle like cosmic dust after contemplating these profound interconnections, remember that you're participating in one of the most remarkable phenomena in the known universe. You are conscious matter contemplating its own nature, aware patterns of information, wondering about the rules that govern information flow, temporary arrangements of quantum fields puzzling over the constraints that make their arrangement possible. The prohibition against faster-than-light travel thus becomes more than just a speed limit. It becomes a window into the fundamental nature of existence itself. It reveals a universe committed not just to physical consistency, but to logical coherence, not just to the conservation of energy and momentum, but to the preservation of meaning and comprehensibility themselves. The speed of light stands as a cosmic constant in the deepest sense, preserving not just the numerical relationships that govern electromagnetic radiation, but the conceptual relationships that allow conscious beings to understand their universe. It protects the foundations upon which all knowledge, all wonder, and all conscious appreciation of reality ultimately rest. As your awareness begins to drift toward the threshold of sleep, carried along by the gentle rhythm of these cosmic considerations, remember that the same elegant constraints that prevent faster-than-light travel also create the stable foundation upon which this moment of contemplation becomes possible. The universe has chosen logical beauty over exotic possibilities, ensuring that consciousness can arise in a reality structured to reward curiosity and wonder with ever-deepening understanding. The universe's commitment to preserving causality becomes even more remarkable when we consider how it operates across the vast scales of cosmic evolution. From the first moments after the Big Bang, when the entire observable universe was smaller than a proton, to the present day where galaxies drift apart at accelerating rates, the same fundamental prohibition against faster-than-light travel has remained constant, unwavering, absolute. Imagine the early universe, a seething cauldron of energy and possibility where the very concepts of space and time were taking shape. In those first fractions of a second, as inflation stretched quantum fluctuations to cosmic proportions, the speed of light limit was already embedded in the fabric of expanding spacetime, ensuring that even as the universe grew at exponential rates, causality remained intact. This cosmic inflation itself provides a fascinating example of how the universe can appear to violate its own speed limits while actually preserving them. During the inflationary epoch, space itself expanded faster than light, carrying distant regions beyond each other's causal horizons. But this expansion didn't violate relativity because it wasn't matter or energy moving through space. It was space itself that was growing, stretching like a balloon being inflated. The distinction is crucial and elegant. The universe found a way to achieve faster than light expansion while preserving the causal structure that prevents temporal paradoxes. Regions of space that were once in causal contact became forever separated, unable to exchange information or influence each other's evolution. The cosmic speed limit wasn't violated, but rather enforced on a grand scale, creating the causal horizon that defines our observable universe. This inflationary history reveals something profound about the relationship between cosmic expansion and temporal consistency. As space expands and carries distant galaxies away from us at ever-increasing speeds, those galaxies eventually cross what cosmologists call the Hubble horizon, the distance at which recession velocity equals the speed of light. Beyond this horizon, galaxies appear to be moving away from us faster than light, but they're actually being carried away by the expansion of space itself. The mathematical elegance of this solution becomes apparent when we consider what would happen if matter could actually move through space faster than light. Such motion would create the temporal paradoxes we've explored, allowing effects to precede their causes and threatening the logical consistency of cosmic evolution. But by limiting faster than light effects to the expansion of space itself, the universe achieves rapid growth while preserving causal order. Recent observations of the cosmic microwave background radiation, that ancient light from when the universe first became transparent, reveal exquisite patterns that reflect the quantum fluctuations present during inflation. These patterns show no evidence of causal violations or temporal anomalies, despite being stretched from subatomic to cosmic scales by the faster-than-light expansion of space. The precision of these cosmic patterns suggests that the universe's protection against temporal paradoxes operated with extraordinary accuracy even during the most extreme phases of cosmic evolution. The same quantum effects that prevent faster-than-light travel today were already operating during inflation, ensuring that the cosmic microwave background carries a coherent record of the universe's earliest moments. But the story becomes even more intriguing when we consider the role of dark energy, that mysterious force driving the current acceleration of cosmic expansion. Dark energy appears to be stretching space at an increasing rate, suggesting that the universe's expansion will continue to accelerate indefinitely into the future. This accelerating expansion creates what cosmologists call the cosmic event horizon, a boundary beyond which events will never be able to influence us, no matter how long we wait. Light emitted from beyond this horizon will never reach us because space is expanding too rapidly for the light to make progress against the cosmic flow. The cosmic event horizon represents a kind of ultimate speed limit imposed by the universe's own expansion. Even if we could somehow circumvent the local prohibition against faster-than-light travel, we would still be limited by the global expansion of space, which creates causal boundaries that no amount of exotic physics could overcome. These cosmological considerations reveal that the prohibition against faster-than-light travel operates on multiple levels simultaneously. Local physics prevents faster-than-light motion through space, while global cosmology creates expanding boundaries that limit causal influence across cosmic distances. The universe protects causality through both intimate quantum effects and vast cosmological processes. The relationship between these different scales of protection suggests something profound about the mathematical unity underlying physical law. The same principles that govern the behavior of subatomic particles also shape the evolution of the cosmos as a whole, creating a consistent framework that preserves causal order across all possible scales of space and time. This unity becomes particularly apparent when we consider how quantum effects in the early universe influenced the large-scale structure we observe today. The quantum fluctuations that existed during inflation, governed by the same uncertainty principles that prevent faster-than-light communication, became the seeds from which galaxies and galaxy clusters eventually formed. The universe thus carries within its current structure a record of how quantum causality constraints operated during its earliest moments. Every galaxy cluster, every cosmic void, every large-scale pattern we observe reflects the influence of quantum effects that respected the fundamental prohibition against causal violations. Modern dark matter and dark energy surveys are revealing this cosmic structure with unprecedented precision, mapping the distribution of matter and energy across billions of light years. These observations show a universe that evolved in perfect accordance with causal constraints, with no evidence of the temporal anomalies that would arise if faster-than-light effects had ever disrupted the cosmic timeline. The concordance between these observations and theoretical predictions based on causally consistent physics provides compelling evidence that the prohibition against faster-than-light travel has operated throughout cosmic history. The universe we observe today could only have evolved as it did if causal order was preserved at every stage of cosmic development. But perhaps most remarkably, the universe's protection against temporal paradoxes extends even into the realm of cosmic speculation and theoretical possibility. Every proposed mechanism for achieving faster-than-light travel, from Alcubierre drives to traversable wormholes, encounters not just local physical obstacles, but cosmic constraints that emerge from the large-scale structure of spacetime itself. Consider the challenge of creating a stable wormhole that could serve as a faster-than-light shortcut between distant regions of space. Even if we could somehow obtain the exotic matter needed to hold such a wormhole open, we would still need to contend with the expansion of the universe, which would tend to stretch the wormhole and potentially close it before it could be used. The cosmic expansion creates a kind of temporal pressure that works against the formation of stable, faster-than-light pathways. Any attempt to create a permanent shortcut through spacetime would need to overcome not just local physics, but the global dynamics of cosmic evolution, adding yet another layer of protection against causal violations. Similarly, proposals for Alcubierre warp drives face not just the challenge of creating exotic matter, but the problem of navigating through expanding space. The warp bubble would need to maintain its integrity while moving through a cosmic medium that is itself evolving and expanding, creating additional technical challenges that multiply the already impossible energy requirements. These cosmic constraints suggest that the universe's protection against faster-than-light travel isn't just a feature of local physics, but a fundamental aspect of cosmic architecture. The prohibition operates simultaneously across all scales, from quantum effects in the vacuum to the global expansion of spacetime itself. The mathematical consistency of these multi-scale protections points towards something even more profound about the nature of physical law. Perhaps the universe isn't just described by mathematical relationships, but is itself a kind of mathematical structure, one that maintains its own internal consistency through mechanisms that operate across all possible scales and theoretical frameworks. This mathematical view of reality suggests that the prohibition against faster-than-light travel emerges not from arbitrary constraints imposed on an otherwise free system, but from the logical requirements of mathematical consistency itself. The universe chooses mathematical coherence over exotic possibilities, ensuring that reality remains logically comprehensible across all scales of space and time. Recent developments in computational physics have added fascinating new dimensions to this mathematical perspective. Computer simulations of cosmic evolution, running on the most powerful supercomputers available, consistently reproduce the observed large-scale structure of the universe using only causally consistent physics. These simulations treat the universe as a vast computational process, with each particle and field evolving according to mathematical rules that respect the fundamental speed limits imposed by relativity. The fact that these computations successfully predict observed cosmic structure suggests that the universe itself might operate as a kind of cosmic computer, processing information according to rules that automatically preserve causal consistency. The computational view of cosmic evolution raises intriguing questions about the relationship between information processing and physical reality. If the universe really does operate as a vast information processing system, then the prohibition against faster-than-light travel might reflect fundamental limits on information transmission that apply to any conceivable computational process. Just as earthly computers are limited by the speed at which electrical signals can propagate through their circuits, the cosmic computer might be limited by the speed at which causal influences can propagate through spacetime. The cosmic speed limit becomes not just a constraint on physical motion, but a fundamental limitation on information processing in the universe as a whole. This information-theoretic perspective connects the prohibition against faster-than-light travel to deep questions about the nature of computation, consciousness, and physical reality. If consciousness itself emerges from information processing, then the cosmic speed limit might be intimately connected to the very existence of conscious observers in the universe. The universe's commitment to preserving causality thus becomes a commitment to preserving the conditions necessary for consciousness to arise and flourish. The cosmic speed limit doesn't just protect abstract logical principles, it protects the information processing capabilities that make conscious thought and experience possible. As we drift deeper into these interconnected mysteries, we begin to see that the relationship between faster-than-light travel and temporal paradoxes touches on fundamental questions about the nature of existence itself. Why does the universe maintain such strict consistency? What principles govern the emergence of conscious observers capable of contemplating these deep questions? The answers may lie in the profound mathematical harmony that underlies all physical law. The universe appears to be constructed as a self-consistent logical system where every principle reinforces every other principle in maintaining coherent, comprehensible reality. The prohibition against faster-than-light travel represents just one aspect of this vast web of logical consistency. Recent theoretical work in quantum gravity and cosmology has begun to reveal how these different aspects of cosmic consistency work together. The discreteness of quantum mechanics, the curvature of spacetime, the expansion of the universe, the flow of thermodynamic time. All of these phenomena appear to be interconnected aspects of a single, unified description of reality. String theory, with its extra dimensions and exotic mathematical structures, provides one framework for understanding this unity. In string theory, all the fundamental forces and particles emerge from the vibrational modes of tiny strings existing in higher dimensional space. The theory naturally incorporates both quantum mechanics and general relativity, potentially resolving the apparent conflicts between these two pillars of modern physics. But even in string theory, the prohibition against faster-than-light travel remains intact, enforced by the mathematical consistency requirements of the theory itself. The extra dimensions don't provide escape routes from causal constraints, but rather add new layers of protection against temporal paradoxes. Loop quantum gravity offers another approach to unifying quantum mechanics and general relativity, suggesting that spacetime itself has a discrete, granular structure at the smallest possible scales. This quantization of spacetime geometry might impose fundamental limits on how precisely we can manipulate causal relationships, providing yet another mechanism for protecting temporal consistency. Both string theory and loop quantum gravity reveal that the prohibition against faster-than-light travel isn't just a feature of our current theories, but appears to be a robust characteristic of any mathematical framework capable of describing a self-consistent universe. The cosmic speed limit emerges as a fundamental organizing principle that shapes the possible structures of physical law itself. These theoretical insights suggest that the universe we inhabit represents one of the very few possible mathematical structures capable of supporting conscious observers. The precise combination of quantum mechanics, relativity, thermodynamics, and cosmology that governs our reality might be necessary for the emergence of complexity, life, and consciousness. The prohibition against faster-than-light travel thus becomes part of a vast cosmic selection process that determines which mathematical structures can give rise to universes containing conscious beings capable of understanding their own existence. The cosmic speed limit doesn't constrain our universe. It helps define what kinds of universes are possible in the first place. This anthropic perspective on the faster-than-light prohibition connects it to some of the deepest questions in cosmology and philosophy. Why does our universe have the particular constants and laws that it does? Why are these constants apparently fine-tuned to allow for the existence of stars, planets, and life? Why is the universe comprehensible to the conscious minds that arise within it? The prohibition against faster-than-light travel might be part of the answer to these profound questions. A universe where causal consistency was negotiable, where temporal paradoxes were common, where effects routinely preceded their causes, might be incapable of supporting the stable information processing required for consciousness to emerge and persist. The cosmic speed limit thus emerges not as an arbitrary constraint, but as a fundamental requirement for the existence of conscious observers. The universe protects causality because causality protects consciousness, and consciousness is required for the universe to know itself through the minds that arise within it. As we rest in the gentle contemplation of these cosmic mysteries, we begin to appreciate the extraordinary privilege of being conscious beings in a universe structured to remain comprehensible to conscious minds. The same mathematical principles that prohibit faster-than-light travel also ensure that this moment of understanding is possible, that questions can be asked and answers can be found. The cosmic speed limit stands as a testament to the universe's deep commitment to logical beauty, to mathematical consistency, to the preservation of meaning itself. It reminds us that some boundaries exist not to limit possibility, but to preserve the very foundations upon which all possibilities rest. In the quiet space between thoughts, as your awareness touches these profound interconnections, you participate in one of the most remarkable phenomena in the known universe. You are conscious matter, contemplating the rules that govern consciousness, temporary patterns of information, wondering about the principles that make information processing possible. The prohibition against faster-than-light travel becomes a window into the fundamental architecture of existence, revealing a cosmos committed to maintaining the conditions necessary for understanding itself through the conscious beings that emerge within its mathematical structure. The cosmic speed limit preserves not just causality, but the very possibility of conscious appreciation of causal beauty. As your thoughts begin to settle like stardust in the vast darkness of contemplation, remember that the elegant constraints preventing faster-than-light travel are the same constraints that make this moment of wonder possible. The universe has chosen mathematical harmony over exotic chaos, creating a reality where conscious minds can arise and marvel at the profound interconnectedness of existence itself. The cosmic speed limit reminds us that we live in a universe governed not by arbitrary rules, but by mathematical relationships of extraordinary depth and beauty. These relationships don't imprison us but liberate us, creating the stable foundation upon which all understanding, all wonder, and all conscious experience of cosmic mystery ultimately depends.